Welcome to this webinar of the BioRecover project. Welcome everyone. Thank you for attending to this webinar. Today with us we have some of the colleagues from the project, and additionally I would like to. We are very pleased to have with us Jarno from UFTT Research Technological Center in Finland. And as the first step of this webinar, I'm going to start with a short presentation of the BioRecover project. I'm going to focus on the problem because my colleagues are going to talk about the solution that this project offers. And our guest, Jarno, is going to talk about a different solution of the NEMO project at the end of this session. Okay, the introduction of the BioRecover project. First of all, I would like to present my organization. We are the coordinators of the project. I am Pablo Frieiro from the European Projects Office of CETIN. CETIN is a technological center in the northwest of Spain. As I mentioned, we are the coordinator of this project. We also participate in many projects at national and international level. And we have 3 knowledge areas, which comprise advanced materials, eco-biotechnologies, which is the area involved in BioRecover, and also digital industry. We are a foundation, non-profit, and a research and technological organization from the classification of the European Commission. Okay, to start sharing some ideas about what is the project of BioRecover, I'm going to start thinking what do these images have in common? You can think about it. As we see, there are different stages of the human history, and the materials are always present. The stone at the beginning, the metals with the tools, after that the industrial revolution with the energy, the coal, the materials to develop the machinery. When the physics and the chemists started to know the matter and the properties of the matter, the nuclear era, the very peaceful applications. And nowadays we have these materials that can transform the solar energy into electricity, and we are experiencing the green tech revolution, the transformation from the coal and the fossil fuels to the green energy and the digitalization of the society. This requires a lot of materials. All the things that we have, all the technologies that we have require a great amount of critical materials, the engines, for instance, the microchips, the chemistry, the pharma technology, the solar panels, the wind energy, everything needs materials. We need a lot of amount of materials. So we can see there are a group of materials which are these rare earths, these elements in the periodic table, which are part of a mobile phone. As you can see in this image, a lot of these elements are part of these devices that we have in our lives, in our day-to-day. But a lot of applications related with the green technology, with the twin transition, depend on these materials, in these rare earths, in these metals, in these other sources like manganese, magnesium, graphite, and everything works with that. Batteries, fuel cells, wind energy, engines, robotics, a lot of things that are the new technologies depend on that. And we don't need materials, but they are limited on Earth. And we can explore new sources in the future, but it is science fiction. We cannot go to the asteroids to do mining. We have to use the things that we have on the Earth, at least to the next 50 years. And this is the world map. And this is the map that worries the European Commission, because most of these materials are not abundant in Europe. Most of these materials are obtained from foreign countries. We depend on these sources, we depend on these countries, and we need that to do our products and to improve our lives, and especially to do our green revolution, to change the energy sources, to use batteries, and to develop these new energies. That's the problem, that we need these materials, but the processes to obtain that are not very environmental friendly. And this is where the BioRecover proposes a solution. On the left of the screen, you can see the main challenges, the impact of the extraction, the low availability in Europe, as I mentioned before, the low concentration of these materials, because you have to treat tons of matter to obtain grains of these elements, of these special critical raw materials. And of course, it has a high cost. From these challenges, the solutions that the BioRecover process propose are to use low-impact processes based on biotechnologies that my colleagues are going to explain in the next sessions of this seminar, enabling new material sources. We can open new material sources in Europe. We can find new sources to avoid the dependency from abroad. And we can improve the yield, the selectivity, and the purity of the process, provoking a dramatical cost reduction associated to the technologies that were currently used. In a nutshell, I'm going to talk about the specific points of the BioRecover project. We are going to use different sources of materials, as we can see in the left of the screen, including bauxite residue from mining, magnesium low-grade ores, palladium group metal sources from mining, and other feedstocks from the pharmaceutical industry and other industries. With this, we are going to do three main stages. The first stage is to remove what is not interesting. We are going to use biotechnology, bacteria, and other living beings to remove the things that are not interesting, to purify. The second stage is the treatment for mobilization. This is to capture the interesting elements of the materials. And in the third stage, we are going to selectively recover the materials, to purify them, to use it. And the last stage of the project is to apply these materials, testing in some of the applications, like in the automotive industry as braking pads or oxygen sensors, or obtaining raw materials from magnesium. In order to do that, we develop lots of technologies that are going to be described by my colleagues in the next sessions of this webinar. Last, I would like to mention that the consortium of BioRecover involves different kinds of organizations, including universities and research organizations, like the University of Copenhagen, Linnaeus University, and University of Coimbra, mining companies like Magna or Mytilineos, engineering and biotech companies like Técnicas Reunidas, Alga Energy, they are with us today, Johnson Matthey, and consultancy and service companies like LGA or Enso Innovation, and end users like FAE, which is in the automotive sector, to test the materials that we are going to develop. I also would like to mention the colleagues from South Africa. South Africa is a region, as you may know, where mining is very important, and we have two universities from South Africa, the University of Witwatersrand and the CIBER from the University of Cape Town. It's a research center. And this is the main idea of the project in a nutshell. And now I'm going to give the floor to my colleagues from the University of Coimbra, who are going to explain the solution in more detail. I focus on the problem. They are going to explain the solution. My colleagues are Paula Moraes and Romeu Francisco. And before, I would like to talk about the upcoming events. We are going to have two more seminars in this series at the end of this year and the next year, but we are going to mention that again at the end. Thank you for the attention on this introduction. We are going to move to the next colleagues. Now I give the floor to Romeu and Paula, who are with us from the University of Coimbra, from the Research Center of the Department of the Life Sciences in this university. Thank you.
Thank you. Hello, everybody. I will ask Capucine to turn on my slides, and it's not possible doing from here. Yes, Capucine? Okay.
Yes, I am sharing the receipt.
Okay. Thank you very much. So I think you can show the next slide, please. We start this seminar by talking about the diversity of microorganisms in the residues, and then we will try to convince you that they are very good biotools and that they will be used in the future to get metals from residues. So starting, I want to say that this is a presentation from the group of the environmental microbiology from the Department of Life Science in the University of Coimbra. We work in the BioRecover project, and our talk will focus on microorganisms that are able to remove interferent compounds from the residues. So starting, I want to say that 300 million tons of mining and quarrying waste are produced annually. Therefore, we need sustainable waste management. And these strategies for sustainable waste management should focus on allowing the residues to be used as secondary sources. Due to the demand on metals, tailings can be a secondary source for critical metals. So this allows not only a sustainable supply, but also promotes recycling. To do it, we need innovative methods and processes for efficient extraction of metals from these residues. So metal-enriched environments, independent of being natural or anthropogenic, are known to include microorganisms. Therefore, mine residues, they also have their own microbial communities, which are composed by organisms adapted to metal-containing environments. These organisms are able to play a role in the natural occurring biohydrometallurgical leaching processes. The microorganisms are able to mobilize metals from solids and also are able to immobilize. So we need to explore the microorganisms in order to make them tools. So the first step for, next slide please, for using microorganisms is trying to, next slide please, Capucine.
Yeah, det var ikke litt.
Okay. So I can, okay. So the first step to be able to use microorganisms is isolate them and be able to know the community. So our first aim in this work was studying the diversity of the microbial community present in the different residues. The second objective was by using biostimulation of the natural microbiota or by using bioaugmentation with autochthonous microorganisms, we aim to evaluate the potential to increase the content in the target critical metals by removing the interfering metals from the residues. We used two residues, one from the exploitation of aluminium and one from the recovery of magnesium. Next slide, please. So our residues are both very alkaline residues. They are magnesite residues and bauxite residue. From the magnesite residues, we have two different samples, FBO and FZU, both with pH around 9. And from bauxite residue, we have a residue with pH 13. Both residues are include or are rich in calcium carbonate and iron oxide. Most the second one. Next slide, please. Okay, so we start by trying to characterize the microbiome of the residues. We start here by showing you the organisms and diversity present in the bauxite residues from Mytilenus in Greece. We isolate the organisms at different pH using a dilute medium. So we recovered heterotrophic organisms. Different pH we select for different group of organisms, but we were able to recover organisms from the genus Dietsia and from the genus Nocardiopsis from all pHs. The biomass was quite high, which is comparable to the biomass that we found in soil, since the residue had between 10 to the 4, 10 to the 5 CFU per gram of residue. Next slide, please. Here we show the diversity of the sample FBO from the magnesite residues from the Magnesitas Navarra in Spain. As you see, we follow the same approach. So we use medium at different pH that recover different heterotrophic organisms. As you can see, there are more diversity here, and we were able to isolate the organisms from the genus Rhodococcus and from the genus Arthrobacter from all the pH that were used. The biomass was a little bit lower, and it was around 10 to the 5 CFU per gram. Next slide, please. A third sample, also from the Magnesitas, it's not on the screen yet, is the FZU sample. We also characterize the organisms that were able to be recovered in our medium, which is designed for heterotrophic organisms. And we found that from these residues, that we got the highest diversity when we recovered the organisms at pH 11. The biomass was a little bit lower, with 10 to the 3, 10 to the 4 microorganisms recovered per gram of residue. And we found mostly organisms from the genus Pseudomonas and from the genus Peribacillus. Next slide, please. So after constructing the collection of organisms, we decide to explore their ability to do something. So we know the diversity, now we want to know what they do. So we decide to try to find organisms able to solubilize carbonates, magnesium, and iron. So we use the medium YDC or YDM or YDFA, which is iron from goethite. And we find quite a number of organisms able to solubilize magnesium and also to solubilize iron from goethite. But the number of organisms capable of solubilizing in the Petri dish calcium carbonate from this medium, from YDC, was quite low. You can see the genus of which belong to organisms that we have isolated and they were able to solubilize the different ions. They belong to the genus Nealia, Holococcus, Metabacillus, and Aeromicrobium. But we were not, let's say, convinced that we would find other organisms able to mobilize calcium and magnesium. So we decided to explore the ability to find new organisms able to mobilize these ions by bioinformatic way. So we use organisms that have already the genome sequenced and introduce them in a bioinformatic pathway that use their genome to characterize the metabolic networks of these organisms. So we decide to target this, to find these metabolic networks in order to explore these organisms, since this could be a way to find more interesting bacteria. So I give the floor to Romeo.
Okay, next slide, please. Picking up on what Paula just said, we then performed some essays. Next slide. On a selection of organisms. These organisms were selected based on COVME and well, that's the potential metabolic pathways that the organisms could perform. We're looking with the software, the ability to assimilate carbonate. No, you jumped 2 slides, I think. Yeah. Oh, yeah. You jumped 1 slide. So first, we performed a test on calcium carbonate directly, and we tested 1 representative strain of each of the genera that were isolated, and we selected the strains that managed to leach calcium more rapidly and in a higher extent. So we ended up with a selection. Next slide, please. Okay. So Capucine, if you can move to the next slide.
Yeah, I'm sorry, there is a delay. I moved already. So.
Oh, okay. Okay, so thank you. So next we move to batch assays. That we performed batch assays with a change of medium regularly for new medium, and we performed a cascade batch leaching assay, and we tested our strains on bauxites, the strains that were selected with CARVME, and we also tested a consortium that was built upon the results that were obtained with the plates, the YDC and YDM plates, and also the leaching of iron on goethite. And we, so here you can see the consortium that was used and the isolates that were used on bauxite. So the consortium was used on FBO, residue FBO, and the isolates were used on bauxite residue. So the parameters that we followed were metals dissolved by ICP, and we also followed the change of solid residue by XRF, and we also used a colorimetric method to follow dissolved calcium. And if you can change to the next slide, please. So all the experiments used 1% of pulp density, and of course we also followed the pH and the connectivity. So here are the results that were obtained with bauxite residue with the isolates. What we can see is that the pH did not actually drop. There was no significant acidification. In fact, all the pHs in the final at the end of the experiment were above 7. I must say that the bauxite residue has a pH of 13, which is quite a lot, and but we started with a pH of about 8. So concerning the XR, by looking at the results of the XRF, we can see that some calcium disappeared. That calcium disappeared when compared to the original residue, and the leaching of calcium was confirmed by colorimetric methods, and we were not really happy with the leaching of other elements. So okay, but at least we had some calcium being leached. So next slide, please. So next slide. Next slide, we can see the. Okay, we sum up the results here. So the classification of bauxite residue, in fact, was not really linked to the strongly linked to the strains that we tested. It was mainly driven by biostimulation. It was driven by the autochthonous community of microorganisms. We saw in one of the cases some help provided by one of the strains that we inoculated, Microbacterium chitamiensis. And the extent of calcium that was removed was between, well, was around 25,000 ppm, about 12%. So next slide, please. Concerning residue FBO, we also managed to see by XRF some calcium being removed from the residue. The pH also, here the pH dropped a little bit, about below 7, and the magnesium contents of the residue was in fact enriched. Can you move to the next slide, since we are running out of time?
No.
Oh, previous one. So here we can see that the consortium, here we use the consortium of 3 strains, in fact, that the consortium managed to remove about 40% of the calcium that was in the residue. It was a reproducible experiment, and the magnesium was enriched by about 11%. Okay, so finally, the last slide. Yeah, there is a lag. I'm sorry. So in the last slide, we can say that the autochthonous microorganisms were mostly responsible for between 25,000 to 50,000 ppm removal of calcium. In one of the assays, the assays with the isolates, the assay the length of the assay was of 4 days only. Okay, and the assay with the consortium was performed during 18 days. But anyway, those incubation times were quite low. So our experiments showed some removal of calcium carbonate without a huge drop of pH. There is also a decrease of silicon, but the removal of the leaching of iron was not really very consistent. Anyway, we ended up with a residue that was enriched in critical metals such as magnesium from magnesite. So I would like to thank all the last slide. I would like to thank all that participated in this work, our partners that sent us the samples, so Magna and Mytilineos, and we also want to thank the University of Copenhagen, and of course other students, well, some students that we also have working with us, Beatrice, Rito, and Leonor. Okay, that's all. Thank you.
Thank you, Romeo. Now we have 5 minutes for questions to be on the schedule, more or less. I don't know if among the public someone wants to ask something. You can raise your hand or put the question on the chat if you are shy to speak. Let me check. I don't see any raised hands. If not, I have prepared a short question. Jarno wants to ask something of our guest. Jarno, please, go ahead.
Hello. Yeah, I have to ask something. This is Jarno Mäkinen from VTT. Thank you for the great presentation, excellent work. What happens to the calcium after the leaching process? Do you have any use for the calcium, or do you have any zinc for that material after leaching? Thank you.
To have the calcium, which now we don't have. If it's solubilizing the medium, we are not testing.
I understand that after a certain point it could be a problem because it will reach certain concentrations that would be counterproductive, right? But for now we're just trying to find something that really works and could remove some calcium. The next step would be to, of course, extend this reaction in time and have a sustainable process. So perhaps we would have to find a sink of calcium. Yeah. But for now, since we were working in batch assays, it was okay, it suited us. It suited our patterns.
It looked very good results actually. I was just thinking if you can, for example, recycle calcium to calcium oxide or some useful chemical if it's not tightly bounded to the leachate form. For example, if you have some bioproduced molecules that bind calcium, so could you produce slaked lime or something that could be used in industry otherwhere? But just ideas. Nice work. Thank you very much.
I can see, for example, phosphate doing that work.
True.
Yeah.
Thank you for the question.
Thank you.
Thank you. I don't know if there are any other questions. No? Okay, then we are going to move to the next speaker. It's Mark Dobson is a professor of microbiology from Linnaeus University in Sweden. He studies the metal mobilization from mineral and waste, among other topics. Dobson has over 20 years of experience in the field and has coordinated 2 European projects related to metals and mining. Mark, the floor is yours.
Thank you very much for that kind introduction. Don't need to do it myself. My name is Mark Dobson. This is a talk about BioRecover treatment strategies for CRM mobilization. Can I have the next slide, please? There we go. So I'd like to say right from the start, this is a synthesis of the work package 3 work. This is not just me or my group at Linné University. We also have SETIM involved, University of Witwatersrand in Johannesburg, and SIBA. And the role that Linné University has had is microbial characterization, the bioleaching assays, and to begin with process optimization. SETIM has been working with bioleaching and the process optimization. Witwatersrand have been doing the same things with different ores, and SIBA have a different role in that they have been doing modeling of the different processes. Can I have the next slide? Thank you. So as has already been introduced very nicely, thank you. So I won't spend a lot of time on this. We've been using various wastes and ores. We have a bauxite residue from Greece, which is a product of the Bayer process. And the target metals we have in here, you can see there, scandium is the main one, and it is associated with iron-rich minerals. And as has been already said, it's alkaline, it's mostly iron oxide, and they are in very fine particles. Can I have the next slide, please? So then we're also working with the magnesite byproducts from Magna in Spain. And this is for the manufacture of magnesite, magnesium carbonate, and hydroxide. And the target metal is the magnesium. And we've received quite a few wastes. I'm not sure how many it got up to in the end, but we've then started to characterize these, look at their various properties so that we can select representative wastes of the different process. And we're just now concentrating on 2 or 3 of these different wastes. Can I have the next slide, please? So the last group we're looking at is the platinum group element minerals. This is from South Africa and also manufacturing byproducts from Johnson Matthey in the UK. And again, of course, we're looking primarily at platinum. Can I have the next slide, please? So we're using bioleaching, and taken off Wikipedia, the definition is a technique of extracting metals from ores and other solid materials, typically using prokaryotes, fungi, or plants. So this is a biological process, and they have general methods. You can have the regeneration of an inorganic oxidant in a catalytic cycle between biological and chemical components. And this is typically like in metal sulfide ores, where the microorganisms are not actually the ones breaking down the target wastes or minerals or ores. It's a chemical process that's catalyzed by microorganisms. Then you can also have biological generation of an organic metal chelating or binding agent that breaks down the target solid, releases the metals into solution. Or you can have a third method of biological generation of an acid that breaks down the target, releases metals into solution. And what are the goals here? Well, the goals is to extract target metals with high recovery and in high purity. Sorry, can you go back? Haven't finished. So as I said at the start, this is a biological strategy. So the things you need to think about here, these are the microorganisms, prokaryotes, fungi, plants. In BioRecover, we're focusing on prokaryotes and fungi. And so we're releasing metals into solution, and these are toxic in many cases. So some of the things you need to do is you need to think about metal toxicity to the microorganisms. And this gets more of a problem as you get more of the metal into solution. You need to think about pulp density in a biotechnological process. So the pulp density is how much of the mineral is in your reactor. As the mineral is being turned and mixed, it can be abrasive. And especially with bacteria, they can break the bacteria particles if you have too much of the solid in there. And then you also need to think of what the end product is. The metals, it's not just metals, they have anions, and these can influence your downstream targets recovery. So it's not just a case of getting the metals into solution. There is a number of other factors in optimization that we need to take into consideration. Now can I have the next slide, please? So what are the biorecover strategies? Well, one is to produce organic acids, and the example I've got here taken from the literature is the production of gluconic acid, for example, by Gluconobacter species. And you get the organic acid can break down the target metals or waste, or put the metals into solution, but gluconic acid is not the only example. There are many other organic acids that can be produced, and also it's not just an acid effect. The biology also plays a role, because if you take organic acids and leach and to extract metals from a chemical process compared to a biological process, in many cases the biological process is better. So the biology is playing a role. What can it be? It can be metal chelators, it can be other factors, but it's not just a chemical process. Can I have a next slide, please? A second strategy we've looked at is biological production of sulfuric acid. And we can do this by oxidation of sulfur compounds. And the example I've got here is again taken from the literature, but it is the production of sulfuric acid from sulfur by a microorganism called Fermi acidithiobacillus cordus. It is an acidophile, so it grows optimally at low pH, so it likes the acid that it's producing. For an acidophile, it has quite a high generation time, about 2.5 hours, and it can push the pH down to about pH 1. And this sulfuric acid can attack the mineral. And we have also been testing the use of a biologically produced sulfur. So this is a waste product from another industrial process, with the idea that we hope what we can do is we can take a waste product, use a biological process to make sulfuric acid to treat another waste. Next slide, please. So we have also done some microbial characterization in work package 3, but as has been described in the previous talk, the majority of the work has been done in work package 2. We have been looking at indigenous microorganisms, but with a different goal. What we've been looking at is for microorganisms that are able to break down the wastes and ores to be able to release the target metals. We've used culturing-based techniques. We grow them on plates, as you can see in the slide on the top right. And we've also done some DNA sequencing techniques and looked at the microorganism based on the DNA in the environment and what they are predicted to be able to do. In some cases, what we found, as was described in the previous talk, in that many of these wastes are very alkaline, and they typically do not have microorganisms that produce large amounts of acid. So in some cases, this has not been so successful, but in other cases, particularly for the PGM concentrates, we have found good candidates for the leaching experiments. Can I have the next slide, please? So then we also used another strategy, and we used an abiotic chemical screening strategy. And the reason we did this is that we wanted to see which acids efficiently break down the target wastes and ores. And then we can then turn to the biological process, and we're guided by these experiments to be able to say, okay, we know that this organic acid efficiently breaks down that waste or ore, and therefore we should find a biological process that's able to do it. And what you can see in many of the cases, we're reaching up to 90% dissolution with these various acids, whereas the water control is down around 5%. So these acids are breaking down and releasing the target metals. So then we think, okay, which ones are good? And we take a biological process that's able to do that. So if we switch to the next slide, please. So I've taken one example here, magnesium dissolution from the magna wastes. And we have efficiently managed to get the magnesium into solution. It's occurring in just a couple of days. You can see that even after 0 time, in some of these cases, it's already have a large amount of magnesium in solution. And the reason for that is these are alkaline, but we're using microorganisms that produce acid. So therefore we have to pre-acidify to get down to a pH that these microorganisms are able to grow. And that's already putting some of the magnesium into solution. In an industrial process, this would be a continuous process, and therefore the microorganisms would continually produce the acid and be able to leach the target wastes and ores. So moving on to the next one. So this is the modeling work, and the goal of the modeling is to describe and predict the dissolution of the critical raw materials and to get data from literature and also the experiments that we have done to model it, get best fit data, and then to fit them to the experimental results. And then this modeling can be used both for process verification and process optimization. Can I have the next slide, please? So here's some of the results of modeling. What you can see is glucose consumption and glucanic acid production on the 2 top slides, and this is using Aspergillus niger as the biological process. We've also looked at microbial kinetics for growth in sulfuric acid by Fermi acidithiobacillus cordus. We've looked at extraction kinetics for the magnesium waste dissolution in different acids, and implementing population balance, incorporation particle size, particle age distribution within reactors. And from all this, a preliminary pH control strategy by acid addition by magnesium waste dissolution has been developed. Can I have the next slide, please? So then from all this, once we decided on our strategies, once we picked the microorganisms, once we've got the basic idea, we go into process development and we look at different strategies. A one-step strategy where you have the microorganisms and the waste in a single bioreactor. We can also look at a two-step strategy where you have the biological production in one reactor and this is then fed into another reactor containing the target wastes and ores, which has some advantages. It separates the microbes from, for instance, the toxic byproducts. It makes metal recoveries downstream easier, but disadvantages that, as I described earlier, the biological process, it's not just the acid produced, there's also some synergistic processes going on. And also you're building 2 bioreactors as opposed to 1, so you're going to have higher costs associated with a separate system. Some other things were also, sorry, too fast, Capucine. A couple of other things we're still working on is optimizing conditions, looking at pulp densities. As I mentioned earlier, as you increase the pulp density, this can obviously make it a more efficient process, but in the sense of you're treating more of the waste and the ore in one reactor, but it can also cause problems with, for instance, a buildup of toxic compounds and metals. And we're also looking at adaptation of the microorganisms. Can I have the next slide, please? So to wrap this up, we've characterized microorganisms on the wastes and ores. We've found candidate species for the bioleaching and contaminant removal. We've used abiotic experiments of acid and cyanide leaching to guide our biological experiments. We've been successful in getting the CRMs into solution. We have these promising strategies. We're now moving into optimization and eventually process design for an industrial scale reactor. And one last slide, please. And of course, I'd like to acknowledge the European Union, and of course, none of this work has been done alone. We have all these different partners working together. Thank you very much.
Thank you, Mark. Now it's time for questions. I don't know if someone among the public wants to raise his or her hand. Nothing in the chat. I can. In the public, no, nobody wants to say anything. I can ask some questions because I want to share some ideas with all the people here, and not a specific question, but as I see, we are developing a technology for specific cases because it's the scope of the project. We are limited to some cases, but the idea of using microorganisms to mobilize these critical raw materials, as I mentioned before, there are a long list of critical raw materials, and some of them are rare earths that can be mobilized. My question and my idea is if we can export this knowledge to other cases, if the project is going to enhance a new possibility to move the technology to other cases, or how we can expand this to other cases.
Of course, all development in this area, the publication in the literature eventually put it into the public domain. We can use these strategies on other wastes and ores. We're building a knowledge base within Europe. We're building experts in the field throughout the entire project. So of course, this can be valorized to other critical raw materials, other wastes, other ores, and build the knowledge base within the European Union. Absolutely. And do you want specific examples?
No, I was thinking, but maybe it's possible to say another example. I don't know, the lithium in batteries, or maybe for lithium there are other strategies, but I'm thinking about the other rare earths that we can find in all of these microchips.
That's what I was thinking. A lot of work has been done with microchips, electronic waste. There is good potential, yes. These same microorganisms, the acidophiles, the microorganisms that grow low pH, as we will hear in the last talk, are being used in metal sulfides. They've also been used a lot in electronic waste, these sort of things.
Or another example that I was thinking are the engines, the electronical engines, where we have magnets. I don't know if it's possible to apply this biotechnology to recover metals from old used magnets, or because recycling is another idea, the recycling of materials, the recycling of devices, as you mentioned, the recycling of electronic devices, but maybe could it be applied to recover these rare earths, that especially in magnets?
I'm afraid I can't answer that. Let's just be honest.
Okay,
I don't know.
Maybe I was going too far, but I was thinking on the main, to solve the main global problems here in an evening at home quietly. Okay, I don't know if someone wants to add something or to ask another question among the public. Okay, then another point that could be highlighted is that in some cases we are using the microbia that are living in the samples. Which this is so relevant? Or is there any alternative? This question is directed to Mark, but also to Paula and Romeo if they want to answer, because which is the main point of using the living beings which are in these samples?
Well, the most obvious answer, the clear answer, is that these microorganisms are already adapted to these environments. So if you have a microorganism living on or in the waste, such as bauxite residue, then they are going to be adapted to that environment. And they also are adapted to maybe not in the bauxite residue, but in some cases being able to use it as an energy source. So therefore, they are if you want to find a microorganism to do a particular process, go to the environment where it happens. Do you want to add something, Paula?
Okay. Yes, definitely. One of the ability of one of the most positive things of knowing the microbiome of these residues is actually knowing organisms that have metabolism that are completely different from the ones that we are used to see. So we have a lot of novelty to know, so a lot of things to explore, and a lot of mechanism of metabolic pathways to explore. And these metabolic pathways are developed by the microorganisms or are selected by the microorganisms because they allow them to live in the metal environment. And if we know these metabolic mechanisms, maybe we can explore them, and maybe we can use these different metabolic ways to obtain the metals from the environment. So I think that microorganisms that live in these metal contaminated environments are able to deal with the metals. So changing the metals from solubilization to precipitation, they use as Mark show us, in a way of getting energy, but also in a way of mineralization, and in a way of trying to obtain some, for example, some metal elements which can be cofactors for enzymes that are much more efficient with a special metal than with another, and these special metals sometimes are not so so normal or present in the normal environment.
Yeah. And in terms of helping or not, well, some can be used to improve the processes, but I imagine that if you are, for example, using an heterotrophic organism, and you add it to that sample and it has autochthonous microbes, they will compete for that carbon source. And so if they don't do what you want them to do, they will, of course, compete with the bacteria, the microorganism that you added, and you may lose some efficiency of the processes. Right, Mark?
Yes, I agree. Hopefully, well, in some of the processes we've been looking at, certainly with the magnesium, we're pushing the pH down close to 1. So the typical microorganisms that live in those environments won't survive. So, okay. And we also, the energy source is sulfur. It's an inorganic energy source. So that isn't so much of a problem, but it can be a problem in many cases, yes.
Yes, if you switch the pH to acids, then you will cause a huge stress on that autochthonous population, because they are used to alkaline pH. Exactly. So yes. That's a good way to get rid of competition.
Control the competition in the process, absolutely.
Okay, thank you. The microbiology is fascinating. As we can see, there are living beings in these samples. There are bacteria who can live in the stomach of a whale, or who can live in a volcano, and they can live also in these samples, and they can help us to recover these critical raw materials. We have an interesting comment in the chat from Clarence. He's pointing that this organism could help to the obtention of nanoparticles. And this is an interesting point. It's not a question, but it's a nanoparticle from the... Yes, he mentions the adaptation of the microorganisms for nanoparticle production. And this is a point that could be studied in the project too. Thank you for the comment. Okay, if nobody has anything to add, I'm going to move to the next speaker. It's Irene Jarama from Alga Energy. She's a chemist like me. She's specialized in analytical chemistry. She's a culture and laboratory technician at Alga Energy since 2020, and she also has experience in other companies in the biotechnological sector, carrying out different research projects related to atmospheric pollution. Irene, the floor is yours, please.
Okay, thank you, Pablo. Good afternoon. My name is Irene Jarama Martin, as Pablo said, and I am laboratory technician in Alga Energy. I'm going to talk about the part of BioRecover project that has been carried out in my company, Alga Energy. Most industrial effluents contain large amounts of heavy metals, toxic organic compounds, and surfactants, which end up causing a major environmental problem. Textile industries, for example, eliminate quantities of metal ions in their wastewater. Conventional treatment methods for these industrial leachates include precipitation processes, ion exchange, and electrochemical methods. The drawback of this type of methodology lies in the fact that they are high-cost processes that are not profitable when large volumes of industrial waste are treated. As an alternative to them, more efficient and economic processes have been proposed, making use of different microorganisms, such as bacteria, yeast, fungi, or microalgae. Among all the microorganisms mentioned, microalgae have very interesting biological characteristics, such as high photosynthetic efficiencies, simple structures, and the ability to grow well in extreme conditions of high salinity, nutritional stress, and high temperatures. Next slide, please, Capuchin. The main objective of this project is to carry out the research and development of an innovative, sustainable, and safe process based on microalgae biotechnology for the recovery of a variety of critical raw materials from secondary and primary sources that have not yet been exploited. The following critical raw materials are intended to be recovered with high recovery capacity, selectivity, and purity, using microalgae as a biosorbent. Rare earths, mainly yttrium from bauxite residues, magnesium from low-quality minerals with silicon or limestone impurities, and calcination byproducts and platinum group metals, platinum and palladium, from low-quality ores, from flotation tailings, and from slag and dust. Next slide, please. Microalgae are unicellular and photosynthetic microscopic organisms capable of inhabiting both terrestrial ecosystems and aquatic ecosystems in fresh or saltwater. This ability to adapt to different habitats over time has given rise to a wide variety within this kingdom, with more than 50,000 species now today. They can exist individually or in chains, ranging in size from a few micrometers to several hundred microns. The structure of microalgae differs from one another, although they share a cell wall made up of starch, glycogen, cellulose, hemicellulose, and polysaccharides. Thanks to these compounds, microalgae are also able to participate in metal absorption processes, since they are capable of forming bonds with metal ions. Next slide, please. The cultivation of microalgae begins on agar plates. On these plates, the microalgae remain dormant for several months, growing slowly. Once the microalgae have grown, they are transferred to a liquid medium that contains the necessary nutrients for their growth and survival. The growth of the microalgae has to be done progressively, going from small volumes, 50 or 100 milliliters, to larger volumes, approximately 5 liters. Next slide, please. In general, the ground cure of a microalgae has 4 well-differentiated phases over time. The development of the different phases will depend on the temperature of the culture, the light source, the composition of the medium, the size of the inoculum, and the characteristic of each strain. The first phase is the growth, induction, or delay phase. Is the adaptation phase. When a strain is inoculated in a new medium, the growth is not recorded immediately, but prior adaptation by the microalgae is necessary. This phase usually lasts up to about 3 days, depending on the state and size of the inoculum. If a strain that was previously well concentrated is inoculated, the time in the induction phase will be shortened. The exponential phase takes place once the cells have adapted to the conditions of the medium and the culture begins to grow exponentially. This phase can be prolonged more or less in time depending on the strain and the incubation conditions. The next phase is the phase of relative growth decline. It's the stationary phase. In this phase, cell growth is practically null and the microalgae remains in a dormant state. In some cases, this phase is so short that it's barely appreciated and the cell death phase directly follows. And the last phase is the cell death phase. In this phase, the number of nutrients in the medium is practically depleted and the existence of cellular debris, bacteria, fungi, and foam cause the final death of the culture. Next slide, please. Absorption experiments have been carried out with free microalgae and with microalgae immobilized on polyurethane supports. Depending on the metal, better results have been obtained in one way or another. The experiments have been carried out with synthetic leachate prepared in the laboratory and with real leachate from bauxite industries. Experiments have also been carried out with monometallic solutions to evaluate the absorption capacity of the different metals individually. Next slide, please. The qualitative results of these experiments can be seen in these images. Significant color changes were observed in the different microalgae after incubation with the leachate. In some cases, these color changes are due to the production of pigments typical of certain microalgae, whose cellular structures is altered after contact with metals. If observed under a microscope, certain aggregations can be distinguished, especially in the case of contact with yttrium. Next slide, please. In terms of absorption percentage, as an example, we can see the graph for monometallic solutions. The specific case of palladium stands out, with absorption percentage greater than 90%. Next slide, please. There are some factors that influence the absorption process. Biological factors. These are factors that depend on the microalgae, such as the condition of the culture medium, the structure of the microalgae, the cell pre-treatment processes, etc. Microalgae that grow optimally in saline medium are capable of developing a greater number of polysaccharides than freshwater microalgae. This fact, together with a greater number of functional groups on the surface, can favorably influence the absorption of metals. The physicochemical factors are the factors that depend on the process itself, such as the pH of the initial solution, concentration or lineage and the metal, contact time, temperature, etc. If the pH of the solution increases dramatically, or the metal concentration is so high that the solution is close to saturation, a process of microprecipitation can take place. In this way, the precipitation of the metal can negatively influence the absorption process. pH is also an important factor to consider, as it can affect the functional groups on the cell surface. Next slide, please. The next steps of the project focus on experiments with other ways of immobilizing microalgae, such as alginate spheres. In addition, new experiments have to be carried out with more leachate from other industries. So far, the result seems very promising. So research will continue along this line with the BioRecover project. Next slide, please, Capucci. This is all for my presentation. Thank you all very much for your attention. And if you have any questions, feel free to ask me.
Thank you, Irene. I don't know if someone has any question among the public. I don't see any raised hand. Okay, I have a question. I wonder, Paula, please, you can ask your question before if you want.
Thank you. Thank you, Paul. My question is related, as far as we have some problems with the network, but as far as I can understood, we talk about spheres of yeah, sorry, alginate spheres. My question is these spheres are for immobilization of the metals on the outside, or you also think about them as a way of as a sponge?
The matrix of containment of the machine.
Yes, this form of immobilization is for the microalgae, not for the metals. It's for immobilize the microalgae, and next try some experiments, absorption experiments with the metals. In this way, immobilize. I don't know if you can hear me.
So you think about immobilizing the microalgae inside the spheres?
Yes. Yes, this is the proposal. Immobilize the microalgae in these supports, and next carry out experiments with these immobilized microalgae in these supports to absorb the metals in this way. And to compare with free cells of microalgae, the absorption of free cells, again, immobilized cells in these supports.
Thank you. It's
of course, alginate also has some. Alginate also has some chelating properties, right?
Sorry, in this support.
Alginate also has some metal chelating properties, right? So by doing this, you also improve the metal chelating capacity of your algae.
Yes. Yes, the proposal is to improve the absorption with this support more than in free cells.
Okay.
Thank you. I don't know if there are any other questions. If not, I have prepared a question. But the idea was to ask, because as we see, the microalgae have the capability to capture the metals, and I was wondering why these living beings do that. Why they do that? What is the biological reason to do that?
Because there are some process in the cell of the microalgae, and it's for the functional groups for the microalgae. Okay, it's for the properties of a microalgae. I can explain more in another occasion, but it's for the characteristics for the microalgae, the polysaccharides, hemipolysaccharides. Is for the properties of the microalgae are better to other microorganisms to this absorption with metals.
And then I suppose that it's like the chemical structure of the I don't know, the surface of the microalgae has functional groups that can chemically interact with the metals, but it's not a biological function. I mean, they don't need, for instance, palladium to do anything with this metal.
No.
No. But they might use another metal from the sea or wherever they live, and they can capture metals. But this, like, they have like a tool, a biological tool to capture these metals by these chemical means of chelating, coordinating these metals, and sometimes, as we can know, the chemistry is not selective. Then that works to capture calcium can capture other metals. That's, I was just thinking about this could be the reason. We have a raised hand among the public. Jose Antonio, I don't know if you can turn on your microphone.
Yes. I can answer some questions that can arising regarding metal transportation in microalgae. There are several factors involving microalgae absorption of metals. Some of them, they are transported from in a specific way, as iron, copper, and many other metals the algae use for their metabolism. But in some other cases, these metals are also attached to the surface of the cell, to the cell wall, because of these components that Irene mentioned before. So there are different processes involved. We don't know exactly which one is involved in which way, but we know for sure that these different mechanisms are involved. For some reasons, there's any specific transport. I mean, a protein, transmembrane protein that are able to transport metals inside the cells, and if they are used for metabolism, but in some way they are accumulated in the cytoplasms. But for some other metals, they are also absorbed to the cell surface through the different components that Irene mentioned in her talk.
And this makes that microalgae have different applications, like, for instance, water treatment, and they are being studied for many uses because of these properties.
For many reasons, for many years, wastewater has been used as a microalgae culture media, and in some way, some different strains have been used to accumulate these metals, and also removing this metal from the environment, from the liquid medium.
Okay, thank you for participating and for your contribution, Jose Antonio.
You're very welcome.
I don't know if we have any other raised hands. No. Okay, then we can move to the next, the last speaker of this evening. It's Jarno is our guest speaker from another project. He's going to present the H2020 NEMO project, and which is another solution for this critical raw materials problem that we are addressing in this webinar. Jarno works as a research scientist at UBTT, the Technical Research Center in Finland. It's a benchmark research center at the European level. He has over 20 years of experience in hydrometallurgical process for low-grade and complex sulfide ores and side streams. And in the NEMO project, he leads a work package about metal and mineral recovery. Jarno, the floor is yours. Thank you for participating.
Thank you. And thank you for the slides. Small correction to the introduction, only a little bit over 10 years, not 20 years. So not 20 years or more like Mark has. But yeah, thank you for the kind introduction. I'm giving a presentation of the NEMO project. The long name of the project is Near Zero Waste Recycling of Low-Grade Sulfidic Mining Waste for Critical Metal, Mineral and Construction Raw Material Production in a Circular Economy. And as you can see, the project is funded by Horizon 2020 by European Union. Next slide, please. So the contents very shortly, I give a general NEMO project presentation, the overall project, and then few slides about NEMO case studies of bioleaching processes done in VTT. Next slide, please. So before going into the details, I want to highlight that we have excellent internet pages, web pages. So if you find anything interesting during the 20 minutes speech of mine, please visit the web pages. You can easily find them by Googling NEMO Horizon 2020 or something. So this is an excellent place. Please visit that. Next slide, please. So what is important to notice in Horizon 2020 NEMO project is that it's an innovation action project, and that means that all research is performed in high TRL, technical readiness level. So we are not actually doing basic research. We are not studying novel technologies too much, but we are piloting, validating and upscaling the processes that have been studied in smaller scale earlier, for example, in previous EU projects or national projects. And also nice to know that project will end this year, late this year. So we have quite much public information articles already available. And that's also why I will keep this presentation very general. So I just want to give you a route how to find the information of the project, all the information, and you can then dig yourself the right contact person that I'm giving to you, and also the things that we are doing. So otherwise I would be speaking the whole night, and yeah, that's not the idea. Next slide, please. So what's the justification in the NEMO project? I think we all know that when we are doing mining of sulfidic ores, we generate huge amount of waste called tailings. And these tailings, it's actually the largest volume of extractive waste in Europe. And if this tailings or this waste is poorly managed, that may cause the environmental problems like acid mine drainage due to residual sulfides in the waste, or other risks like dam breakage, because the tailings are usually pumped to the tailing ponds as slurries. So it's difficult to control, the dams may break down. And EU and EIP have also noticed this problem, this extractive waste problem, and decided strongly that it should be turned to the resource recovery opportunity instead of problem. And one driver, of course, is that these tailings still contain also valuable and critical metals. So Europe wants to use those to markets, not to lose them to the tailing ponds. Next slide, please. The NEMO concept in short is that we want to create a near zero waste processing scheme for sulfidic ores and tailings, and we are using the 4 pilots, 3 case studies approach or concept. And the 4 pilots we are doing work in the NEMO. They are located at the key points of the near zero waste flow sheet, namely leaching and recovery of valuable and critical metals, removal of sulfides and hazardous elements, treatment of the cleaned residual mineral fraction that can be used for construction products, backfilling, or post-closure mine rehabilitation. So the outcome should be of the project that we have been able to reduce the waste amount to only 5% of its original volume. Next slide, please. So in this slide, you can see what we can find from the tailings, sulfidic tailings in general. We have precious metals, we have base metals, we have rare earth elements, and we have critical metals. And of course, we try to recover all these when possible, and depending a little bit of the site that we are studying. At the same time, we have to find a way for safe storage of hazardous materials, for example, arsenic, cadmium, and so on. And finally, the residual solid that we obtain from the process, we have to do something to that material, and we would like to have a building materials like explained earlier, or backfilling or whatever, but not to lose that material, which might actually be quite interesting for us. Next slide, please. So in this slide, the main point is actually on the right hand, you see these blue circles. Very interestingly, if we are talking about tailings and volumetric flow rates of the tailings, sulfidic tailings, 3 classes can be spotted. The recovered valuable metals, they consist only about less than 10% of the total volumetric flow. If you go to the hazardous components, less than 5% of total volumetric flow. And clean mineral fraction can be, well, it's the major share of the volumetric flow. And that's why the clean mineral fraction management of that is also very important. So it's not only getting critical metals or base metals or valuable metals, removing the AMD risk, but also how we use this huge amount of material that can be inert after the NEMO technology. Next slide, please. So the positive side effects of NEMO concept, we try to get the full conversion of sulfides, and that means that we also simultaneously remove or eliminate the risk of acid mine drainage. Also, the conversion of sulfides to sulfates, that can lead to several benefits, like sulfates can be used as a fertilizer products, it can be used in cement, and also we can produce some very expensive products like battery grade chemicals, cobalt sulfates, for example. And the enhanced leaching results in cleaned mineral fraction that allows the use of this huge stream in construction applications like I explained earlier, and also safe backfilling and mine rehabilitation material. And finally, when we master the process, have the full flow sheet, the hazardous elements are no longer diluted into the mineral fraction, but concentrated and safely stored. Next slide, please. So as always in EU projects, we have a very wide distribution of different organizations and countries in EU that are joining. There's just briefly, well, you can see from the table that there's many partners: VTT, Vito, Idener, KU Leuven, Finnish Minerals Group, ThyssenKrupp, Resourceful, BRGM, Skyscape, Jacobs, Cobrellas Cruces, IMNR, Katapa, University of Exeter, DMT and Boliden, and together we are building this NEMO solution for sulfidic tailings. Next slide, please. And this might be very interesting to you. So our aim, as explained, is to do a high technology readiness level research. That means piloting in different chemical or biotechnological processes. So we have 4 different pilot types, or actually these are work package types. And if we check first for the pilot 1 and pilot 2A, these pilots actually gather all the classical bioleaching processes that we can use, meaning that we have a heap bioleaching, we have a pond bioleaching, and we have a tank bioleaching. So all 3 main categories of bioleaching are gathered and studied in pilot and validation. If you go to the pilot 2B and all the group of pilot 3, those pilots concentrate on what's happening after the bioleaching. So that means that we have to purificate the solution, we have to recover the metals. So we have built an extensive pilot setup using chemical precipitation of base metals, for example, hydroxide precipitation, sulfide precipitation. Also, we are checking the solvent extraction route for rare earth elements separation, and also a little bit more novel technologies in sulfide and hydroxide precipitations by changing some chemicals in the processes and so on. But these all are completely chemical systems, not biological. And finally, pilot 4 group is what happens after the leaching also. So what happens to the residual solid, which should be inert. So how we can use that as cementitious materials by flash calcination, artificial aggregates for construction, and concrete for end products. Next slide, please. So I'm not actually going here to the project structure so much. It's much easier to go to our web pages as said, so you can read the full story there. I just say the 3 case studies where the pilots are done. So we are working at the Sotkamo mine in Finland. Also we are working at the Luikonlahti processing plant in Finland and also in Tara mines in Ireland. Next slide, please. Replication potential is very important in EU projects because we are not searching a solution for one mine or one waste deposit. We have to find a solution for EU problem or the problem we have in EU, and that's why we are doing quite much work to find all possible places in EU area where there are sulfide tailings. And we try first to fit the chemical analysis, mineralogical analysis of these sites to our processes and see whether we can use the NEMO project or NEMO processes to solve these challenges. So if you have anything in mind, a site in EU, we would be very happy to hear information of your example, and then we can together check whether NEMO project can help you, and we could distribute the results also. Next slide, please. So I want to make sure that you all know what we are doing in the NEMO project, and you all know who you should contact. Of course, you can always go to web page, as I said, but also I shortly go through the work packages so you see what we are actually doing and who is the contact person. So the work package 1 is innovative bioleaching led by Anne-Gwen Gesenek from BRGM France. And the main work in the VP1 is actually to develop a heap bioleaching or a pond bioleaching. And this is actually going in the quite big scale. There's huge hypes in Sotkamo done by Finnish Minerals Group and the BRGM at the moment. So very, very high tier research taking place there. Next page, please. So the work package 2 is a pilot scale bioleaching of processing residues. So this work package is led by Anders Sand from Boliden. And here the idea is that we use tank bioleaching in order to dissolve or treat the sulfidic tailings with emphasis on cobalt, nickel, zinc and copper. Very high sulfidic tailings. And as said, tank bioleaching, but also we have to work, or this work package 2 is more also to the complete flow sheet of what kind of process we have to build. So the bioleaching itself it's not enough because we got the pregnant leach solution which is poisoned by iron, aluminium, all the unwanted elements. So in this work package 2 we are also working to find the full flow sheet how to build a factory or plant that can treat this sulfidic tailings, meaning precipitation and recovery of metals. Next slide, please. Sorry. So the work package 3, it's metal and mineral recovery. That's led by me. And here the main idea is that what happens after bioleaching. So we are trying to search all the possible solutions, what can be done after bioleaching of sulfidic tailings. So basically that means that, or actually we are not searching for the solutions, but we are piloting and trying to improve the existing technologies. So what that means, we try to improve, for example, sulfide precipitation of multi-metal leachates in atmospheric pressure. We try to do a solvent extraction to recover earth elements from the leachates of the tailings, both in classical solvent extraction way and also by non-aqueous solvent extraction way. And also, as mentioned earlier, we have this a little bit more novel technology of doing oxide and sulfide precipitation, or hydroxide it should be, and sulfide precipitation using ammonia for different base metals, but also to generate products from aluminium and iron group metals and manganese and magnesium. Next slide, please. The work package 4 is concentrating on clean mineral residue upcycling. The work package leader is Jost Lemk from ThyssenKrupp. And this work package is also what is happening after bioleaching, what we have to do for the residual solids that we get. As you remember, it was the main volumetric flow material from the process, so there must be a sink for this material, there must be a utilization possibilities, or otherwise our processes are in big troubles because we have to put this material somewhere. Next slide, please. And of course, like all EU projects, we have supporting work packages. The work package 5, very important as we are speaking about innovation action. All the pilots that we are doing, we have to integrate them to serve the full flow sheet. We have to build process controls, occupational safety, environmental safety, all the documentation, instrumentation, and this is actually a very interesting topic also. And I think this might be very interesting also to many projects that are going to the innovation action, how we can increase the TRL and really show that these pilots are reliable. So this work package is led by Maria Tripiana from IDENER. Work package 6, sustainability analysis, very important in EU projects and when going to the higher TRL, led by Andrea Di Maria from KU Leuven. Then work package 7, we are doing clustering, of course. And next slide, please. And stakeholder engagement in work package 8, also very important nowadays. We have to keep all the stakeholders happy. And work package 9, which is management. So next slide, please. So as said, please visit our website. Here you can see some contacts of the NEMO project, but you can find them all from the web pages and much more information if you're interested. So this was the general presentation of NEMO, and now I will go to the VTT example, what we have done. So next slide, please. So in NEMO project, VTT was given a challenge or order to develop and pilot and validate a treatment process for sulfidic tailing materials. The material that was given to us was high sulfide tailings consisting mainly of pyrite, about 50% of the weight, pyrrhotite, about 30%, and also some cobalt, nickel, zinc, and copper residuals. So the general flow sheet was that the material was treated with bioleaching first, so that was the leaching selection of ours, and we utilized autotrophic microorganisms in anacidic conditions. So I personally say usually this is classical bioleaching. Like Mark Dobson said, there are bacteria that can produce sulfuric acid and inorganic oxidants like ferric iron. And this process uses those to dissolve the sulfides and also the metals that are incorporated to the sulfide minerals. After the bioleaching, we have to go to the leachate purification and metal recovery to get actually some revenues from the process and treat the solution. And our selection was a threefold or three-step process. It starts with the iron and arsenic precipitation with limestone. And after that, we go to the copper, cadmium, and zinc precipitates with hydrogen sulfide gas. And finally, after that, we go directly to the cobalt and nickel recovery with solvent extraction. And the aim is to produce battery-grade cobalt sulfates and nickel sulfates. Next slide, please. So about the bioleaching process that we were working with, the main challenge when we obtained the material was it was very, very recalcitrant. The main interest was in cobalt because it was quite a high level that we still found cobalt, 0.7% from the material. And it was bound to the pyrite matrix, so very recalcitrant and possibly passivated because of being in the tailings pond for some time. So that's why we used additional milling at first before bioleaching. And if you check the figure in the right hand, the first bars illustrate the cobalt leaching yield in the process regarding to the milling time and resulting particle size. You see the black bar there, very poor leaching of cobalt if you don't mill the material. So nothing really happens if you try to bioleach the material without milling. If you apply a little bit milling, you already get more than 70% leaching yield for cobalt. And if you optimize it, you go almost to 100%. So milling is very important sometimes for this kind of materials. If you want to know more about this work, you can always visit our article about this. It's open access, so you can all read it. You can check the slides or this email address from the recordings, or you can just Google my name and milling and bioleaching and you will find it. Next slide, please. As very often when working with sulfide minerals or matrices, bioleaching or this classical bioleaching is an acid producing process, and optimal pH for the bacteria must be maintained with basic chemicals. And limestone resulted in much faster processing compared to sodium hydroxide, and this is actually very obvious because the bacteria we are using in this kind of process, they actually get their carbon from the limestone also, not only the atmospheric carbon dioxide, but also from the limestone. So it's obvious that the bacteria work faster when they get carbon for their growth. Moreover, the limestone is much cheaper, and we can use also impure limestone, while sodium hydroxide is usually a chemical product with a higher purity, higher price. And also if you use sodium hydroxide, we get the sodium problem in the process. We have to have a sink for the sodium. We have to remove it. It's difficult, it's expensive. So simply don't use sodium hydroxide, use limestone. For the process, the optimal pH was around 1.3 to 1.5. What means here optimal is the cobalt leaching yield and also the iron oxidation rate. So if we go below 1.3, the iron oxidation goes slower and we get a slower process. If we go above 1.5, say to 1.8, the iron 3+ concentration goes so high that we easily start to precipitate it as a jarosite and we lose the oxidative power. Again, you can find more information about these from our articles. 2 articles about these from the right side. Next slide, please. The final challenge in bioleaching process with this material was the high pyrrhotite content. The bioleaching process is a highly oxidative process if we are using this autotrophic bacteria. It's a highly oxidative process. And unfortunately, pyrrhotite is a very reducing mineral. So this means that, at least in theory, when we are doing bioleaching for the material that contains plenty of pyrrhotite, the pyrrhotite is dissolving first, and that consumes huge amount of acid and oxidant. And if we use the oxidant and acid for pyrrhotite, we cannot do anything else before the pyrrhotite is completely dissolved. So we have to wait until pyrrhotite is dissolved, and then we can do actual bioleaching work to dissolve, for example, pyrite, which contains now the cobalt. So we try to understand how the pyrrhotite is actually affecting to the total leaching process. So we did some piloting rounds. First, we did a piloting or validation process for non-oxidative sulfuric acid leaching to remove completely the pyrrhotite from the material. So now we have two materials. We have pyrrhotite-free material that is treated by sulfuric acid treatment, and we have a native material which contains the pyrrhotite and valuable metals. Both contain the valuable metals because sulfuric acid is not enough to leach anything from this material, but pyrrhotite. And then we did a bioleaching pilot tests for both materials, the native that contains pyrrhotite and for the pre-leached material that didn't anymore contain the pyrrhotite. And we were quite surprised of the results because bioleaching was clearly possible with both materials. And actually the retention times were quite similar also. So this was actually what we thought, that if you have pyrrhotite, the retention time should be longer, but it was surprisingly small, the difference. So with both materials, with pyrrhotite or without pyrrhotite, the retention time was 6 to 7 days, 6 to 8 days. And also the metal yields were quite similar with both materials. So it seems that we shouldn't remove the pyrrhotite, and our worries were not actually taking place or realizing. However, there are some other questions also, or considerations, because if we are using the bioleaching of native material containing the pyrrhotite, it's a very simple method. We just put the material to the bioleaching circuit, wait for a certain time, use some limestone and oxidation, aeration to do the work. Very simple and plain. But if use this pre-leaching with sulfuric acid, we actually might be able to use the pyrrhotite to produce some sellable chemicals like sulfur and iron. And that's actually quite interesting, but also it goes to the much more complex process, and that means expensive. Next slide, please. Just a few more slides left. So what's happening after bioleaching? We have to purify the solution and take the metals out from the solution to get some profits. So as said, we did first the iron hydroxide and ferric arsenide precipitation. That was successful. We used limestone there, and practically all iron, aluminum, and arsenic were removed. And the main point here was that with optimization, we were able to decrease the losses of target metals like cobalt to be less than 5%. I think the main run was 3% loss of cobalt, which is very good also in industrial terms. After the iron removal, we did the zinc, copper, and cadmium precipitation with H2S gas. That was also very successful. All these three metals were precipitated nearly completely. A slight concentration of zinc was left. Again, very important that cobalt and nickel were not lost in this process. And we are speaking about leached purification here, but actually it's very nice that the product we obtained was very rich in zinc, 68%. I remember there was a little bit copper left and cadmium. That means that we can actually sell this product or concentrate to the zinc plant, at least in small volume. So it's not waste, it's a product that we get the revenues. For cobalt and nickel solvent extraction, we are currently doing studies. There's no public information, so I can't share you anything about this, so you have to wait. Next slide. Here's just a simple picture of our equipment that we were using. So VDT has very flexible piloting facility, we can use these cascade reactors, continuous mode, leaching, precipitation in atmospheric pressures. Nearly all processing can be done in VTT with this setup via bigger reactors, smaller reactors, and so on. Also, we have the solvent extraction pilot. It's not shown in this picture, but 12 mixer settler units. Next slide, please. I think this is the last slide of my presentation about replication potential. The studied bioleaching, precipitation, solvent extraction process was performing really well with the example material of the NEMO process. With small tailoring, the process can be used for nearly all cobalt, nickel, and zinc contain sulfide materials. So just fine tuning, and we can run it for every material. If there is manganese in the feed, we can add a manganese recovery unit to the flow sheet. However, if we are concentrating copper, more tailoring is needed because we have to change the leaching circuit, because low temperature allotrophic bioleaching is not dissolving at least chalcopyrite well, so different leaching process should be used. And also if there's much copper, we have to take that as a product out from the system, and most likely we would do it differently than here. So it's possible, but more tailoring is needed. Next slide, please. Thank you. Any questions? Almost 5 minutes over time. Sorry.
Thank you, Jarno. Now it's time for questions. I don't know if the audience wants to ask some questions or someone. Mark.
Hello there. I have a lot of questions, but you've gone back to my old days.
I have read your papers.
Yes, and I know a lot of the people you've talked about. You talked about pond bioleaching. I just wondered what's developed in that since the last time I looked at it. We looked at it a long time ago with BRGM, and it wasn't considered economical.
Yeah, I have to be careful what I say because it's BRGM's business, so I don't want to say anything too strict, but I think there has been progress. It's still studied a lot, so I think it's very interesting, and for the actual how it looks now and what are the key problems, you have to ask from Gwen about those, but it's studied a lot still, so I think there's potential.
Okay, thank you.
I don't know, is there any other question?
I can ask some more if nobody else wants to have a go.
If you want, you feel free, please.
I was just letting other people have a chance. I'll do one more, then I'll leave it alone. Your sulfide precipitation, so you're selectively precipitating. How are you controlling your selectivity?
The sulfide precipitation, we can control the selectivity by 3 factors. Number 1 is pressure, and now we don't have that because we have to do atmospheric pressure, the sulfide precipitation, which is not actually very typical, but we did it in atmospheric pressure, most likely because of the Finnish origins of that technology, like in Terrafame process in the Sotkamo. So now we have 2 control parameters more or left, pH and sulfide concentration. So we play with these 2 things, and actually it's if you keep the pH low enough before nickel and cobalt precipitation, it's very easy to actually control. You can see it very well that it's actually very difficult to precipitate nickel in the low pH, speaking about pH 2. And when you have to precipitate nickel, when you have removed all the others, then you can raise the pH higher, and then you can get the nickel out. So it's playing with the pH and the free sulfide ion concentration in the solution.
Yeah, we did some papers on that a while ago with biological low pH. Are you biological production of H2S or chemical?
We are doing in chemical ways at the moment in this NEMO project, but we have also old project of this biological sulfate reduction, and yeah, the nickel precipitation there is actually very difficult from my what I have found, but I haven't done it in many years.
Thank you very much.
Thank you.
Thank you. We have another person asking for a question. I think Vitalis. I don't know if you can open your microphone. Oh, we are not hearing you. You are not mute, but we are not hearing you. Maybe you have. Yes, now I think that we can hear you.
Okay, so thank you so much for your presentation. Of course, I'm quite interested. I wanted to make a follow-up question concerning the work that you did on the effect of remilling or pre-milling before the bioleaching. Would you say it was mechanical activation or like renewing of the surfaces? That would be the reason, and also what sort of time frames, like after the milling, was it until you got to the actual leaching?
Very good questions, and unfortunately I don't have clear answers. So it might be mechanical activation or it might be increased surface area, especially if we are speaking about pyrite that incorporates cobalt. It might be very important that we really get huge amount of or very much surface area for leaching, so we can actually pinpoint the cobalt. But if you have pyrrhotite, it also might be that it's because of the mechanical activation. So we didn't study that in details because we don't have in VTT that kind of equipment, and we would have to buy that service from other place. And we also already paid quite a lot of money them to do the milling and other things. So we lost. We didn't have any more money to do that research. But it's a very interesting topic, and we were checking it from literature, but we were not sure how it goes. About leaching, it's very interesting that after the milling, we actually did some tests how the time after milling affects to the leaching yields. And actually, after the milling, the material was quite, the results were quite same if we waited for 1 week or 1 month or actually even 4 months. Of course, we kept the material airtight bags, oxygen removed and in cold. So that might prevent the oxidation of sulfides and these layers of passivation coming, but surprisingly little effect on that. But if we put it there to the sunlight, it will be, of course, oxidated and passivated the material very soon.
Okay, thank you so much. Yeah.
Thank you.
Thank you both. Then I don't know if there are any other questions. If not, we can finish this session. I'm going to share my screen again just for 1 second, just to remind that we are going to have 2 additional seminars in this project. As you can see in the screen, it's expected to have the first one in November, performance, environmental benefits and socioeconomic of novel biomining technologies, and the third one more or less in 1 year, technical and economic improvements of critical raw materials extraction, considering the scope of the project. I would like to thank everyone here, the attendants, the people, guest speakers, LGI for the organization, and especially Jarno for our guest speaker invited from other projects. Thank you for your contribution and your participation. We will be in contact as you are part of our external panel, and I will send you an email in these days. We will be in contact because your experience is an important contribution to our project. And thank you to all of you, and see you in the next events of BioRecover. If you want to keep informed, you can see our website and subscribe to our newsletter. Thank you all, and that's the end of this session for today.
Thank you. Bye-bye.
Bye.
Thank you. Bye-bye.
Thank you.
Thank you. Bye.